So we're not done with oxidation reactions yet. Oxidation and reduction reactions. Okay, so I want to go over a couple of basic oxidation reaction reactions and have you guys go through and balance them. Now, in order to balance a lot of these reactions, you have to kind of know what the activity series of each one of these things are. All right? And what the activity series is a series that deals with the reduction energy. And the higher we go in the chart, the higher the reduction energy that's going to be there. Okay, and that means the reduction energy, ease of oxidation, how easily each of these oxidizes. So if I have lithium solid, that's going to go to lithium plus an electron very easily. Okay, so that means that it's going to be oxidized very easily. The energy that it gives up for reduction is actually quite high. Okay, or it's going to be high in order to get that to reduce, excuse me. So as I go down, you'll see that there are things like sodium. Okay, sodium is going to do the same thing lithium does. Okay, and as we go down the table, we find that it's going to be harder and harder to oxidize some of these things. So we get down to, say, aluminum. Okay. And aluminum is going to go to Al3 plus 3 electrons. Okay, and then we're going to get down to things like iron. Remember, these are the ones that are hard to predict. And if you look at the values for iron itself going to iron 2 plus is going to be lower than the aluminum. And that's going to release 2 electrons. There's also iron 3 plus. It's not on the table in some books, but there's always a larger value or table for this activity series in the appendix of most of the books that we deal with. Okay, and you're going to get down to different other metals like gold. Okay, gold and silver. These ones are really low on the table. They don't like giving up their electrons. This is what makes them precious metals. Okay, they don't like giving up their electrons. They like staying as gold. They like staying as silver. Occasionally they oxidize, but they do that in a very slow fashion for the most part. Okay? So you have to sort of reference one of these tables and figure out what's going to happen with each of these reactions. Now, I don't know if you guys are familiar with anything nautical. And this is a good example of what happens. Okay? But if I have a boat, here's my boat, dude. Okay, there's the boat right there. If it's sailing the ocean itself is filled with salt water. And that salt water, as we see, increases the electrolyte ability inside the water, the ability for the water to conduct electricity. So because of that salt, the iron itself is going to oxidize very easily at this little threshold, where water hits it and it's reacting with oxygen that's in the atmosphere. You're going to oxidize the iron, and your boat's going to rust. Once the boat rusts, the hull becomes compromised. You don't want that to happen. So how do you get around this? Well, the easy answer is don't sail ships. But we got to sail ships, right? So the solution to this is to put little blocks of zinc on the hull of ships. And what these little blocks of zinc do is they prevent the oxidation of iron because they're in contact with the boat, the hull being steel, the hull being iron. They prevent that oxidation because it's easier to oxidize the zinc than it is to oxidize the iron hull. So the first thing that happens is that the zinc is going to get oxidized, and once that zinc's gone, then the boat hull can oxidize. Okay? So it's an interesting little thing as far as what happens in the ocean. Okay? Now, let me put it this way. If I have, say, lithium solid in the presence of something that's oxidized. So I'm going to put, actually, let me not use lithium. Let's use aluminum. Okay? Aluminum is a solid. And if aluminum is going to react with silver, it's going to react with silver sulfate. Okay? In this case, the silver's oxidation number is +1. Sulfur is -2 in this case. Okay? So what's going to happen here in this particular system? The aluminum is going to react with the sulfur to become Al2, and I'm going to get 3 sulfurs out, and I'm going to regenerate the silver that's on the surface of the metal. All right. Now, how does this work? I can't remember if that's aqueous or solid, so I'm just not going to get to that right now. How does this work? You can break this down into half cells. All right. So in both of these cases, the sulfur is -2. So it's not really that important. It's the aluminum that's going to be important. So my half cell, I'm going to break this down to aluminum, right? And aluminum is generally going to be 0 here. And then I go to 2 aluminums, okay? Since I've got 3 sulfurs here, that's going to be 6 electrons that have been ditched. Okay? But because I've got 2 of those there, it's going to be 6 electrons. So what do I have to do to balance this entire thing in the system? That's right, I've got to put a 2 in front of this aluminum. Now it's a balanced system. What about with the silver? Now we have to balance the silver, the amount of silver that we're getting in this system. So I go from silver plus, I started with 2 of these guys, and I'm going to be adding electrons. So right now I'm adding 2 electrons. And what I'm going to get out is 2 silvers. Okay? But I have to make sure that my electrons are going to be appropriate. Okay? Because I can't have free electrons floating around. So I have to make sure the electrons are balanced. So I'm going to multiply this entire thing by 3. So now I've got 6 silver to start with. That means I've got 6 electrons here. And that's going to go to 6 silver solid. All right? So now I have to represent both of these changes up here at the top. Over here I had 2 aluminum, so I've got to put a 2 there. I had 6 of the silver, all right? So I'll put 6 there? No, because I've got 2 there, so it's got to be 3, right? So I'm putting a 3 here. Now I've got 6 silvers on this side, and I'm going to have 6 silver atoms on the other side. Now, does this balance the sulfur as well? Yes. 3 sulfurs over here. Now you're looking at me and you're looking at the video saying, geez, Dr. Ray, we just did the whole thing of balancing. I thought I could do that in my head. That looked easy. Yes, it does. And it looks a lot like balancing right here. But you have to be aware that when we get into electrochemistry in the second semester, it gets a little bit more complicated. So I want you to be able to recognize the 2 half cells. Oh, and by the way, if we look at these half cells, which one is oxidation, which one's reduction? The aluminum is being, that's right, oxidized. Good. And the silver, therefore, is being reduced here. All right? Now, one more thing. When I talk about oxidations and reductions, because I've got 2 things going on, I have to identify them as reagents. And this can get confusing. Okay? So bear with me. If I look at the aluminum here, is the aluminum being oxidized or reduced? That's right, the aluminum is being oxidized, which now makes it the agent that's causing reduction of the silver. So that which is being oxidized is known as the reducing agent. Okay? If I look down here at what's being reduced, the thing being reduced, the silver, is oxidizing the aluminum. So this is called the oxidizing agent. If I ask you this on a test or a quiz, which I will, All right? The easiest thing to do is to write out the half cells, find out which one's being oxidized, which one's being reduced. Do that first. And then find out which one is the oxidizing agent, which one's the reducing agent. Okay? If you know what's being oxidized, you can figure out what the reducing agent is. And once you know the reducing agent, the other one has to be the oxidizing agent if it's a two-component system. Okay? A little bit more. Okay, now here I've got three different reactions of the oxidation reduction type. I've got a synthesis, I have a decomposition, and I have a combustion analysis. Okay? My synthesis reaction, what this one is a combination of two things. When I synthesize things, I take two things, and I put them together and make one large molecule. Okay? So this is a synthesis reaction, and look what's happening over here. What's the oxidation number of nitrogen? Since nitrogen is bound to itself, there's no oxidation value there. Okay? So the oxidation number for nitrogen is 0. What's the oxidation number for hydrogen? Yeah, that's right, it's 0 as well, because it's also bound to itself. When I go over here to NH3, now these hydrogens are +1. So that means the nitrogen is going to be a -3, and each one of the hydrogens is going to be a +1. So what's happened here? The nitrogen has become oxidized or reduced. It went from 0 to -3 as oxidation number. That's right, it was reduced, which means that the hydrogens were the ones being oxidized. Notice here that the nitrogen, which is more electronegative, is oxidizing the hydrogen, which is less electronegative. There might be a connection. Okay? Well, let's look at decomposition. In decomposition, I've got water generating hydrogen and oxygen gas. Okay? The hydrogens here are each +1, and the oxygen is the classic -2. But when I do this decomposition, this becomes a 0, and that becomes a 0. So what happened to the oxygen? It went from -2 to 0. Okay? In order to do that, it had to lose 2 electrons, right? So it's become reduced. All right? And this one over here has been oxidized. I'll put that up here too, that the nitrogen over here has been reduced, and the hydrogens have been oxidized. Now what about for a combustion reaction? And this is why combustion reactions are so energetic, is because they're a redox process. There's electron transfer going on. You don't think about that. You're just like, whoa, cool explosion, right? But down here, I've got something serious going on as far as electron transfer. My carbon over here is -4. It's more electronegative than the hydrogen, so it's got a -4. And the hydrogens are each +1. Over here, my oxygens are 0. Okay? When I combust these things, my carbon, now bound to 2 oxygens, becomes +4. These things are -2 now. This guy is a -2, and these hydrogens are each +1. All right? So what happened to the hydrogens? Nothing. They're +1 over here and +1 over there. So they're not being oxidized and reduced. What is being oxidized and reduced is the carbon. The carbon goes from -4 to +4. So it had to lose 8 electrons. That's a serious loss of electrons. So the oxygen here is being oxidized by the oxygen. Okay? Which means that the oxygen is being reduced at this point. Okay? But these are 3 other reactions. As far as their names go, things you have to know.